Somewhere inside a government warehouse in upstate New York, a piece of hardware originally built for spying on the entire planet sat completely forgotten for years, until someone finally realized it could be repurposed to spy on the entire universe instead. That piece of hardware is about to become NASA's newest space telescope, and it is set to capture more of the sky in a single shot than Hubble managed to capture across its entire 36-year career. Stick around, because the story behind this telescope is even stranger than the science it is about to deliver. This telescope is called the Nancy Grace Roman Space Telescope, and it is scheduled to launch on August 30th, 2026, aboard a SpaceX Falcon Heavy rocket lifting off from Kennedy Space Center in Florida. It is named after Nancy Grace Roman, NASA's very first chief astronomer, a woman so instrumental in getting the original Hubble Space Telescope built and funded that she earned the nickname the Mother of Hubble. Decades after helping create one legendary telescope, her name is now attached to what many scientists believe could become an even more influential one. Before we get into what this telescope will actually discover, you need to hear how it came to exist in the first place, because the origin story alone sounds almost too strange to be true. Back in 2011, the National Reconnaissance Office, the secretive government agency responsible for building and operating America's spy satellites, quietly approached NASA with an unusual offer. Sitting unused in storage were two enormous telescope mirrors, nearly identical in size to the one used on Hubble, originally built for classified surveillance purposes and never actually launched into orbit. The National Reconnaissance Office no longer needed them, and rather than let this specialized hardware go to waste, the agency offered both mirrors to NASA completely free of charge. To put that gift into perspective, imagine the sheer scale of engineering, planning, and expense that went into building the James Webb Space Telescope, and then imagine a spy agency casually mentioning it happened to have two similarly sophisticated instruments sitting around that it simply did not need anymore. NASA accepted the donation, and one of those two mirrors eventually became the heart of what we now know as the Nancy Grace Roman Space Telescope. The second mirror, remarkably, still sits in storage today, preserved for potential future use, though no agency has yet committed the funding needed to turn it into a fully operational mission of its own. Although the mirrors themselves came at no direct cost, accepting them was far from a simple decision. NASA still had to design, build, and pay for an entirely new set of instruments, electronics, and supporting spacecraft systems to actually turn this donated piece of hardware into a functioning space telescope. Engineers spent years redesigning the internal components, since a telescope built for classified surveillance of Earth required a very different set of instruments than one intended to peer billions of light years into deep space. That donated mirror measures 7.9 feet across, almost exactly the same size as the mirror inside Hubble. But size alone does not tell the full story here, because despite matching Hubble's mirror diameter, Roman's mirror weighs less than 1/4 as much. That dramatic reduction in weight makes the entire telescope significantly more agile, allowing it to reposition and retarget much faster than older observatories built with heavier, bulkier components. If a discovery this strange involving hand-me-down spy satellite hardware turning into humanity's next great space telescope is blowing your mind right now, go ahead and hit that like button, because it genuinely helps this channel keep telling stories like this one. Now let's talk about why this telescope has scientists across the entire astronomy community so excited. Roman's defining feature is not raw image sharpness, since its resolution will actually be quite similar to Hubble's. What makes Roman revolutionary is its field of view, the total amount of sky it can capture within a single image. Roman's field of view is at least 100 times larger than Hubble's, meaning a single photograph from this new telescope will cover roughly the same area that would have required 100 separate Hubble images to capture. That difference sounds impressive on paper, but the real-world implications are almost hard to fully grasp. Because Roman can survey such enormous areas of sky in each individual pointing, it will be able to scan the universe roughly 1,000 times faster than Hubble ever could. NASA estimates that within just a matter of months after becoming fully operational, Roman could survey as much of the sky, in comparable detail, as Hubble managed to cover across its entire 3-decade career. Over its planned 5-year primary mission, Roman is expected to cover roughly 50 times as much territory as Hubble examined throughout the whole of its historic run. Behind that massive field of view sits an equally impressive piece of technology. Roman's wide field instrument, a 300 megapixel camera built from 18 separate 16 megapixel detectors working together as a single unified imaging system. Each pointing of this camera will cover an area of sky roughly 1 1/3 times the size of the full moon as seen from Earth, compared to Hubble's infrared images, which typically capture less than 1% of that same lunar-sized patch of sky in a single shot. All of that data comes at a cost, quite literally, in terms of sheer volume. Roman is expected to transmit more than 500 times as much data back to Earth every single day compared to Hubble, and across its 5-year primary mission, the telescope is projected to generate more than 20 petabytes of information. Processing and storing that much scientific data represents its own massive engineering challenge, requiring entirely new systems built specifically to handle a flood of information far beyond what any previous space telescope has ever produced. Engineers and data scientists working on the mission have spent years developing pipelines capable of automatically sorting, calibrating, and archiving this incoming flood of images, since no team of human researchers could possibly review that volume of data by hand in any reasonable amount of time. That scale of data collection also changes how astronomers actually plan to use the telescope. Rather than requesting individual observations of specific pre-selected targets the way researchers often do with Hubble or Webb, much of Roman's observing time will instead be dedicated to broad, systematic surveys covering enormous stretches of sky. Once those surveys are complete, the resulting datasets will be made available to the entire scientific community, allowing thousands of researchers around the world to search through the same archive for their own specific discoveries, long after the original observations were first taken. So what exactly is all of this data actually going to be used for? Roman has 3 major scientific missions guiding its design, and each one tackles a different fundamental mystery about the universe. The first centers on dark energy, the mysterious force believed to be responsible for the accelerating expansion of the entire universe. Scientists still do not fully understand what dark energy actually is, and Roman's wide, sweeping surveys are specifically designed to map how the universe's expansion rate has changed across billions of years, potentially offering crucial new clues about this invisible force shaping the cosmos. The second major mission focuses on hunting for exoplanets, worlds orbiting stars beyond our own solar system. Roman will conduct a specialized survey using a technique called microlensing, which detects the subtle gravitational bending of light that occurs when one star happens to pass in front of a more distant one, briefly magnifying and distorting its light in a very specific, measurable way. If a planet happens to be orbiting that closer foreground star, its gravity adds its own tiny detectable signature to that lensing event. Using this method, scientists expect Roman to discover roughly 2,600 new exoplanets over the course of its primary mission, focusing specifically on the crowded, star-dense region toward the center of our own Milky Way galaxy. This microlensing approach offers a major advantage over other exoplanet detection methods, since it can reveal planets sitting much farther from their host stars, including cold, distant worlds similar in orbit to Jupiter or Saturn, a category of planet that other detection techniques have historically struggled to identify in large numbers. Roman will also carry a second dedicated science instrument called the coronagraph, a specialized high-contrast camera and spectrometer designed to block out the overwhelming glare of a distant star so that any planets orbiting it can actually be directly imaged, rather than merely inferred through indirect methods like microlensings or the tiny dips in starlight caused by a transiting planet. Directly photographing a planet from many light years away is an extraordinarily difficult technical challenge, since a star's brightness typically overwhelms any planet orbiting it by many orders of magnitude, similar to trying to spot a firefly hovering directly next to a blazing spotlight. The third major pillar of Roman's mission involves general infrared astrophysics, using its enormous field of view to study everything from star formation happening within our own galaxy to the structure and distribution of matter across vast portions of the observable universe. Because Roman can photograph such wide areas of sky so quickly, it is expected to measure light coming from more than 1 billion individual galaxies over the course of its operational lifetime, an almost incomprehensible number that would have taken previous telescopes many decades to even approach. Roman will not be operating alone out there either. It is scheduled to join the James Webb Space Telescope at the second Lagrange point, a gravitationally stable location roughly 1 million miles from Earth, where the combined gravitational pull of the Earth and Sun allows a spacecraft to maintain a consistent position relative to both. Working together, these two telescopes are expected to form an incredibly powerful scientific partnership. Roman's wide, sweeping surveys will be able to quickly identify rare, unusual, or scientifically interesting objects scattered across enormous stretches of sky, and Webb, with its narrower but far more detailed vision, can then swoop in to study those specific targets with exceptional precision. That partnership represents a genuinely new way of doing astronomy. Rather than each telescope working in isolation, Roman TALS functions almost like a scout, surveying vast, uncharted territory and flagging the most promising discoveries, while Webb serves as the specialist, following up on those flagged targets with far greater detail than a wide survey instrument like Roman could ever achieve on its own. Together, astronomers expect this combination to reveal far more about the early universe, distant galaxies, and the population of exoplanets scattered throughout our own galaxy than either telescope could manage, working entirely alone. Mission planners have already begun coordinating observing schedules between the two telescopes, ensuring that particularly interesting regions of sky identified by Roman's wide surveys can be quickly handed off to Webb for closer inspection without unnecessary delay. It is worth pausing here to appreciate just how unusual this telescope's entire journey to launch actually has been. What began as classified spy satellite hardware, quietly donated to NASA more than a decade ago, spent years being redesigned, tested, and painstakingly transformed from a tool built for surveillance into an instrument built for pure scientific discovery. Along the way, the mission itself went through several name changes, originally known as W-FIRST, the Wide Field Infrared Survey Telescope, before eventually being renamed in 2020 to honor Nancy Grace Roman's lasting legacy within the agency she helped shape. And now, after more than a decade of development, testing, and careful engineering, Roman is finally ready to launch, arriving 9 months ahead of its original schedule, a rare achievement for a mission of this scale and complexity. Once operational, it is expected to work for at least 5 years, though many scientists anticipate the mission could continue delivering valuable data well beyond that initial timeline, much like Hubble itself, which was only ever expected to operate for around 15 years, and has instead remained scientifically productive for well over 3 decades. That kind of longevity is never guaranteed in advance, but the track record set by earlier NASA space telescopes gives researchers real reason for optimism heading into Roman's own mission. What makes Roman's upcoming launch so exciting to the broader scientific community is not just the sheer scale of what it will observe, but the sheer number of unexpected discoveries that kind of wide-scale survey work tends to produce. Throughout the history of astronomy, some of the most significant breakthroughs have come not from telescopes specifically designed to search for a particular object, but from wide, systematic surveys that stumbled across something nobody was even looking for in the first place. With Roman capable of photographing such enormous portions of the sky so quickly, astronomers fully expect it to reveal entirely new categories of cosmic objects that current instruments simply are not equipped to detect. Some researchers have already started referring to this kind of unplanned discovery potential as the true hidden value of a survey telescope, since the biggest breakthroughs often turn out to be the ones nobody had thought to specifically search for in the first place. There is something genuinely fitting about how this entire mission came together. A piece of hardware once built purely to watch this planet in secret is about to spend the next several years watching the rest of the universe completely in the open, with its discoveries shared freely across the global scientific community. Few missions in the history of space exploration carry quite that same sense of transformation, turning a tool originally designed for secrecy into one of the most open, data-sharing scientific instruments NASA has ever built. Before you go, if this story about a former spy satellite mirror being reborn as one of humanity's most powerful scientific instruments genuinely fascinated you, make sure to subscribe, because there are so many more stories like this one covering the biggest upcoming breakthroughs in space exploration. The Nancy Grace Roman Space Telescope is about to launch into orbit, and when it finally opens its enormous eye on the universe, astronomers expect it to reshape our understanding of dark energy, exoplanets, and the sheer scale of the cosmos itself, all within just the first few years of its mission.